All right, here we are for worksheet 2, problem number 4, okay? Boy and a girl and a pumpkin. It says, hey, a 45 kilogram boy is holding this 12 kilogram pumpkin while standing on ice skates on a smooth frozen pond. We're gonna assume that the friction between the skates and the pond is negligible, okay, on the ice. The boy tosses the pumpkin with a horizontal speed of 2.8 meters per second towards a 37 kilogram girl who is gonna catch it, okay? Girl is also wearing ice skates on this essentially frictionless surface. What are the final speeds of the boy and the girl? All right, so here we go. We're gonna draw our sketch. All right. So here we go. So at the start, this pen is awful. This pen's not much better. Alrighty, so here we go on ice skates. Okay, and he's holding a pumpkin. Okay, and the girl is going to be over here, right? Prepared to catch the pumpkin. Okay, and let's see here, ice skates. All right, there we go, good enough, right? Okay, so that's like the start, okay? What's gonna happen then? Well, the boy's gonna throw the pumpkin, right? All right. Okay. So then that pumpkin is gonna go sailing to the right. Okay. With the speed that we're told is 2.8 meters per second. Yeah. Okay. Toward the girl, who is again prepared to catch that. Yeah, right? Okay, so here we go. Speed is 0, everything at the start. Speed is 2.8. Speed is still 0. What's gonna happen to the boy? When the boy shoves on the pumpkin, force on pumpkin by boy, force back on boy by pumpkin, he's gonna start to drift backwards. There will be some final velocity for the boy there that we're gonna try to find. Okay. Hey, what happens next? Well, the girl catches the pumpkin, right? Okay. So the boy will be drifting backwards still, right? I'm not going to draw that. But now the girl is going to have caught the pumpkin, and together, the girl hanging on to that pumpkin, right? Which is changing shape as we do this. I don't know why. But the point is, she is going to go sliding backwards, right? Okay. And so she has 0 momentum. She's sitting still. The momentum, the pumpkin is coming in. Momentum to the right. Together, they've still got to have that momentum to the right. And so she's going to have some final velocity. Velocity of the girl final. There we go. Right. So that's what's going to happen. Again, the boy is still drifting backwards here. I'm not drawing him in for the third step. All right. So here we go. So when I look at this, there's like 2 interactions going on. There's an interaction between the boy shoving on the pumpkin shoving back on the boy, and there's an interaction when the girl catches the pumpkin between the pumpkin shoving on the girl shoving back on the pumpkin, and then moving together afterwards. So there's really kind of like 2 interactions to look at. However, I'm going to draw them in now anyway, aren't I? Hey, look, remember that the boy is still drifting backwards here, right? Right? I'm gonna do this. Velocity of the boy final, right? Same as here. Yeah? I'm gonna just go, I could do it like in a separate calculation here and a separate calculation, one for the boy and the pumpkin, one for the girl and the pumpkin. But you know what? Let's just do it as one big overall system with 3 objects in the system. Boy, girl, and pumpkin. Okay? So here we go. We're gonna make the system, okay, be all 3 of them. All right? Can I do that? I think I can do that. think I'm gonna be able to do that. Am I gonna be able to do that? Yeah, I guess so. Or we'll set up, we'll see what happens. Can I get away with doing this? Boy and girl and pumpkin. Okay? Let's give it a try. If I do that, sigma, sigma, I just tried to write delta and I said sigma. Force times duration, come on, Dave, is my change in momentum. Okay, you see, if I'm making my system all three, and we're just interested in the horizontal motion here, is there any outside horizontal force acting on the three of them? If we assume that that interaction between the skates and the ice is frictionless, then you say, no, there's no horizontal outside force, nothing to change the horizontal momentum, no horizontal impulse. So this is just going to be the change in the momentum of the boy, the change in the momentum of the pumpkin, of the girl, and the change in the momentum of the pumpkin. Change in the momentum of the boy, right? Plus the change in the momentum of the girl, right? Plus the change in the momentum of the pumpkin. Okay? If I go ahead and let's expand out those deltas. Okay? Am I going to stop color coding? I'm going to stop color coding. This is ridiculous. This will be momentum of the boy final minus momentum of the boy initial plus momentum of the girl final minus momentum of the girl initial plus momentum of the pumpkin final minus momentum of the pumpkin initial. Are any of these zero? And you say, hey, at the start, everybody was sitting still. So all the initial terms are going to drop for us, right? Every initial term is going to drop. Bang, 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 right? So you're like, well, that's helpful. Okay, I think. Is there any other data? I feel like I'm missing some data here. Well, I didn't put the masses on the diagram. I know the masses. That might be important. Oh, yeah. Yeah, I'm not going to be able to solve it in one go. Okay, that's okay. So here we go. Mass of the boy is 45 kilograms. Mass of the pumpkin is 12 kilograms. Mass of the girl is 37 kilograms. Okay, that's not m times g, that's m subscript g, the girl's mass. Okay, there we go. Okay, got it. So if I tried solving this in one fell swoop, going from the very start to the very end, check out what's going to happen now. I'll have 0 is mass of the boy, velocity of the boy at the end, plus momentum of the girl, mass of the girl, velocity of the girl at the end, plus momentum of the pumpkin, mass of the pumpkin, velocity of the pumpkin at the end. The thing is, she's holding the pumpkin and they're moving together. So the final velocities of the pumpkin and the girl are the same. So this variable, velocity of the pumpkin at the end and velocity of the girl at the end, they're the same. All right? So I'm just going to call that velocity of the girl at the end. Okay? It's the pumpkin's velocity and the girl's velocity are the same. So what are my unknowns here? Well, I know all the masses. And these two v's are the same. I actually have two unknowns. You're like, ah, dang it. I've got one equation, but I got two unknowns. I need to somehow get one of these, right, from some other equation. You know how we're going to do it? We're going to make use of this. They told us this velocity the pumpkin had. So we know the momentum the pumpkin had at this point. Well, that's kind of in between the two, right? So I'm going to need to make use of that information to solve. So I'm going to have to either do a calculation from here to here, right? So, or do a calculation from here to here. That was nastier. Let's go from here to here, because here we know the velocities of everything, and they're all elementary zero. It's going to be easier to go here. So let's just look at the interaction of the boy and the pumpkin first, and then we'll come back to this, okay? So let's make our system be now just boy and pumpkin. But in particular, here I was trying to go from, what do you want to call this? Condition A, situation B, situation C. Here I was trying to go from A to C in one fell swoop. But but I need to make use of this information in the middle. Okay, I don't have enough information to solve. I got two unknowns. So let's do this one from A to B. Okay, looking at just the boy and the pumpkin, the girl doesn't come into it because she's not involved. Her momentum doesn't change in this part from A to B. So if I put it in, it wouldn't matter. So here we go. So looking at this again, but you say there is no outside impulse on the two of them combined. There's just a force of the pumpkin and the boy shoving on each other. They're both in the system. So that goes away. So this is going to be my change in momentum for the boy plus the change in momentum for the pumpkin, right, going from A to B. And of course, that's going to be momentum of the boy. See, I should have labeled these spots before, but that's okay. At B, minus the momentum of the boy at A, yeah, sure. Plus momentum of the pumpkin at B minus momentum of the pumpkin at A. You say, but wait a minute, are any of these zero? And you say, yeah, at the start, at position A, those are all zero. So these all drop out. Momentum at position A. So I really just have these two. That look, the momentum of the boy at B and the momentum of the pumpkin at B add up to zero. And so that makes sense. The total momentum at the start is zero. After they shove off each other, the total momentum should still be zero. For these two numbers to add to zero, clearly one of them is gonna have to be negative, yeah? And they're gonna be equal and opposite, right? Gosh, this notation is awful because I got position B and B for boy, P for momentum and P for pumpkin. This is awful notation. But anyway, I think you get the idea. Hey, at this point, do I have the information I need? Let's see, mass of the boy, velocity of the boy at B, plus mass of the pumpkin, velocity of the pumpkin at B. And you say, well look, the mass of the boy, I know is 45 kilograms. The velocity of the boy at B, that's the velocity when he's going backwards. He's going to have that velocity for the rest of the time. That's one of the things I'm trying to solve for. So that's exciting, right? This is what I'm trying to get. Mass of the pumpkin, we know what that is, 12 kilograms. Velocity of the pumpkin at B, oh, that's that 2.8 they gave us. Hey, we know all the values of velocity, but we can find that velocity of the boy after he interacts with the pumpkin. Let's do that right now. Am I going to rearrange? Let's just put the values in. So I'll have 0, mass of the boy, 45, times the velocity of the boy at position B, plus mass of the pumpkin, 12, times the velocity of the pumpkin at B, 2.8 meters per second. Okay, punching in my calculator, I can get that velocity of the boy at the end here. Times 2.8. Okay, and if I do that, I get this negative 0.747. Do we want that negative sign? Yeah, we do. The velocities, the boy's heading in the negative direction. I really should have labeled my coordinate axes right away. I shouldn't have in my sketch. He's going in the negative direction. We want that negative there. Hey, that's the velocity he has after he shoves the pumpkin. He's sliding back now. We're ignoring friction. He's going to have that same velocity the whole rest of the time. That's the final velocity of the boy. That can go in here. Now, in this equation, we can solve for that final velocity that the girl and the pumpkin have together. Okay? So now, looking at this equation, sorry, I'm at the bottom of the board here. I'm just going to move this to here, okay? So I'll have 0 equals mass of the boy, velocity of the boy at the end, that's that negative 0.747 that we got, meters per second, plus mass of the girl, 37 kilograms, times the velocity of the girl at the end that we're trying to find, plus mass of the pumpkin, 12 kilograms, times the velocity of the girl at the end, the girl and pumpkin together. These are the same variable, that have the same velocity at the end, the girl and pumpkin. Hey, I can solve that equation for that VG final. If I did that, rearranging, move this term to the other side, the sign and flip would become positive. 45 times 0.747 divided by 37 and 12, right? Factor that out, divide it out. Okay, punching that in my calculator, Okay, and I get 0.686 meters per second, which seems to jive. Okay, the velocity comes out to be positive, which makes sense. She and the pumpkin are moving in the positive direction, and that's that problem. So I couldn't go from start to end of the whole thing because I ended up with two unknown velocities here and here. But because they gave me information in this intermediate state, I could calculate from start to the middle, right, to find that velocity of the boy, and then plug that back into this overall equation. I also could have, instead of doing an overall A to C, I could have done A to B for the boy, and then I could have done maybe like B to C, the girl catching it, as like a separate calculation. And that would have been fine too. All right, that's problem 4. Problem 4.